Thanks, Olivia, for the invitation. Very glad to be here. So maybe I can give you maybe some background about the company that you may be not familiar with. So Huawei is a big constructor of internet infrastructure, so switches, base stations. And now it has a presence in Paris, where it's a group of 60 people covering all aspects of wireless and wired mathematical modeling. This is joint work with colleagues that are at Huawei, at Eurofond, George Pashus, and CMOS Toulouse. So the main objective of the lab is to support the activities of Huawei in 5G wireless networks. So 5G wireless networks is the next generation of networks. It's wireless networks that will be deployed from 2020, probably. And the aim is to really alleviate congestion in the system. And this is due to an increased amount of data that's being used in the system. Most of it is video. And so there are many constraints that come from latency, so the time it takes you to access content, and also aspects related to bandwidth optimization. You don't want to be moving content from remote locations too often. So one of the ways to solve this problem, and other problems that are related really to the wireless medium itself, is densification of systems. So have many more base stations than there are today. They are usually called femtocells. And the problem I will focus on here is really how to place content as close as possible to the user to optimize latency, okay? The time for a user to access content. And so the idea, so this is kind of what the problem that we were given when I joined the lab is, if I put some storage on base stations, how can I use that storage to store data that's relevant to people that are in the vicinity of that base station to be able to kind of get data directly rather than go and pick it up from some remote data center. And this is also due to kind of the fact that storage is easy to deploy, so we can deploy a lot of storage throughout the network. Okay, so here we're faced so the problem is like being studied a lot in already wired systems, so there are already caches deployed all over the internet. One famous company is Akamai that does this, so it places storage, for example, there's one around Paris, and it stores the content that's most demanded by the people in the region Paris, rather than if you like wanted to have something, to have them go and fetch it from the US or from other countries. And so the issue when you are starting to do localized content distribution networks is that if you wanted to use statistics about the user demands, they are too sparse, or the samples are too small for you to be able to do anything that's statistically significant. And so the hit rates, that means the probability that something that is in the cache is actually requested by someone in the vicinity of that cache can be very small. So one of the questions I tried to address is how to achieve good hit rates for small local caches. So this is like the geographical issue. The other issue, which is already common in the context of general CDNs, is the temporal locality, whereby traffic that's demanded by people, or content that's demanded by people, is generally ephemeral, so it can have maybe a few hours, or like the bursts of demand of traffic can be short-lived, and then you want to track these changing popularities over time, and so how to do this also in this context. So there is a standard online simple algorithm that's used for solving this for CDNs, which is called LRU, which is least recently used, and there's also another one which is least frequently used, and variants of this are the ones that are used for standard CDNs. So this problem of caching, local caches, has been studied a bit in the literature. So there's a whole literature around doing coding to be able to do those caches. I'm not familiar with any of that, so I'm not going to mention that. I'm just going to mention things that are closer to the solution I'm going to propose. So there's a work by people at Imperial, Denis Gunduz and Paul Glasgow, that propose a kind of Knapsack Bandit approach. They have a very simple model where each cache has a certain probability, each content has a certain probability of being demanded at any given time. They have different sizes, you have finite capacity, and you want to learn the popularities and store them to be able to maximize it. There are people also who propose side information. So for example, if you are able to predict that something is going to be demanded, then you just kind of prefetch it and load it in the cache. And so they use things, data from like social networks and Twitter, seeing what people are talking about, and then use that to preload data. And there's a very recent work by Masoulier and other people from INRIA that propose sort of market mechanisms to optimize here not latency but bandwidth. So here you want to be fetching, so that the content you have at some point to go and get it from the data center to the cache, and they want to minimize actually how much of this is happening, data being moved around. So what I'll talk about in the remainder is a way of solving this problem. So there are like a number of steps that we go through. First of all, like to optimize latency, often maybe what you need is not necessarily to cache the whole file, but to cache the first chunk, a sizable first chunk of the file that will enable you sort of to get user to access that, and then it's going to start pushing the rest. You could do better than first chunk. We have an ongoing work that looks at popularity of chunks because people don't watch movies in a uniform way. They kind of jump around, and you want to kind of put the most appropriate chunks. But here we're just going to focus, like there is a chunk from the file that I'm putting. So this kind of just scales the size of the storage. And to solve the time variation of the traffic, I'm going to define a threshold policy to store content in a given cache. And then I kind of talk about how to leverage local knowledge and global knowledge. Maybe something I didn't emphasize. So if you were to use, and I'll show this in a minute, if you were to use the, for example, aggregate information from different caches to decide where to push the caches, you're just going to see different distributions that are merged together. This might not be relevant to your specific local cache. So really what you want to do is really to make the content within a given location tailored to the demands in that location. So I'm going to define a model that could be debated. So this is a model that's kind of often considered in the literature, and it's been shown that it's empirically matches existing mobile content data. So this is a very simple Poisson short noise model of how the content arrives and lives in the system and is demanded. So that the way to define this is that there are shots that arrive at, so the shots are the squares here, that arrive at sort of Poisson process with some rate. We're going to do the simplifying assumption that any traffic has a lifespan of capital T. So the T bars here are the arrival times, the capital T is the duration of the shot noise. I'm going to also assume that throughout the shot, so for example, for shot 1, there's a parameter mu1 that's related to it, that's drawn from some power law distribution. This kind of represents popularity of content. And then inside the shot, there's a Poisson process of which rate is this rate here. So often this alpha is 0.8 empirically. So this is kind of what I, so content arrives, there are demands, these are the errors here, and then it departs. Okay? And so we'll assume that we know the TIs and what follows, but we don't know the MUIs, and we want to optimize this, not knowing the MUIs. So the assumptions I'm making is that we only store the first chunk. We know that we said that the controller, so the person that makes the decision for this cache knows the exact arrival times, and there is no cost for replacing content. Okay, this kind of complicates things if you add cost to replacing content, but there are sort of things that one could do. And the goal is to maximize hit rate. So hit rate is really, as I said earlier, the ability to get content directly in the cache rather than having to fetch it from further away. So fraction of demands found in the cache. Okay. I'm just going to introduce some notations. So we're going to define the age of the content as at a given time t, which is just how long the content has been around until it kind of goes all the way through the system. And I'm going to look at a given time t, what's the number of requests for that content at the time natural to get. And I'm going to define ym_t is the indicator whether I'm going to have content m in the cache at time t or not. And the challenge is to optimize kind of average hit rate. I put t here, but sort of because of stationarity it doesn't matter. So I'm going to optimize the kind of instantaneous hit rate for this, for the cache. Okay. So if I knew the μm's, what I would do is that I would just store the ones with the highest μm until I fill the cache, but I don't know the μm's. So in fact, what I will do is that I'm going to try to look at what's the expected value of μm, knowing its age, and knowing the number of the months that I have. Okay? So one could just take the ratio, like the empirical number of the months so far, but that's kind of maybe give us sort of something that would be very varying, and you have to change content all the time. So we take an age into consideration to make sure that older content have more chances of being kept because we have a better understanding of its popularity. So this is just simple algebra to compute the expression of knowing the nm's and the tau m's. So the number of requests up to time t and the age of the content, and we can simply compute the expectation of this based on the assumptions of the problem. And the algorithm goes as follows. So the idea is really to do the following: to have some idea of what's the distribution of the μm's, and then to cache content that has popularity that is above this parameter here, c over lambda t, which is the fraction of the catalog that could be stored in the cache. And so the threshold to define is defined as this: is for a fixed age, there will be so this is something that can be computed based on the previous equations. We are looking at the smallest k, the smallest number of the months for a content of type tau that is larger than this. And we only cache content whose number of the months is larger than until the tau m. So content that has h tau m will only store if this condition is satisfied. And then to just make sure that we respect the strength of the cache, we only, if we have more than C contents that have this property, we only take like C of them. So this is the algorithm. So the threshold is a complicated expression to compute. So when we explained this to the engineers who asked us about this problem, is they told us, well, how would you compute this? So we told them that you can sort of just pre-compute things and then use that, or use sort of heuristics that are quite popular in this area, which is to do like auto-filling, which is just increase the threshold, so the threshold, so that sort of you see hit rate increasing, and then once it sort of starts saturating, you start decreasing a bit. Okay? So you really sort of move the threshold around to try to tailor it to the content popularity and the other problem parameters. So one thing that we managed to prove is that if we consider the optimal policy, so the policy that would know the thetas and would do the optimization, if you look at the optimal policy, online policy, then we can show that in the regime where C and lambda, so the number of demands and the content size go to infinity, but sort of in a similar way, that C divided by lambda t converges to some gamma C, then the policy was the optimal policy will converge to our policy, to be this age-based thresholding. So that's kind of a reasonably interesting result. And then, so this is kind of explains how you would do the one cache. So you have just one cache, and then here really you're solving the temporal issue of storage content. The second thing to deal with is if you have multiple caches. Okay, so here you have multiple storing units that receive demands, and you want to kind of make sure that you're able to store what's relevant to the specific location. So one simple thing is that if you have no correlation between these locations, then you can only do very little, and then actually you're just always lagging behind.
So just something you don't understand. So isn't there a big difference between the regime where lambda is of smaller order than t, and when it's bigger than t, than capital T?
So the results we have here are for, yeah, absolutely. If you have a lot of content arriving, and then they stay for a long time, then you clearly very quickly figure out what the news are, and you can work on that. The other way around is that so if you have lambda large and t small, then you don't get to see enough of it. So that's why we have them like of the. So sorry, I said t goes to infinity. Lambda and t go to infinity.
Lambda and t go to infinity.
Yeah, sorry. Yeah.
And with what? How exactly? With what ratio?
So the lambda and t go to infinity where the ratio is constant like this. So they have a concentration. They are similar actually. So that's why it works. Sorry, it's t. So I was saying, like, if the traffic is uncorrelated between different locations, there's no hope to do anything more clever than doing actually aggregating them. Let me just kind of define quickly a model that we came up with. This is like really very tight model. It just includes geographical relationship between different caches to be able to leverage their similarity to improve hit rates. So we're going to assume that each cache, each content will have a popularity mu that depends on the content itself, but also on the location. And then we assume that contents have some feature vector, and location also has some feature vector, both lines 0, 1, and we define a kernel that tells us sort of correlations between location and content. Okay, so there are there's a relationship, like if you are in the 16th in Paris, then you're more likely to look at some type of content compared to if you were like in the 5th or the 4th. And so we define the local content as, so this is the global popularity of the content as an aggregate. And here, this is something that we just kind of normalized by the sort of propensity of content can be watched in L. And so, so here the issue becomes that you don't know. The issue is that you don't have enough samples to be able necessarily to get this mu ML, and then you want to be able to use the relationship between different locations that you would learn over time to be able to cluster those, and then aggregate their join demands. So here we're just not going to look at the learning part, but we look at the aggregation part. So whether like local learning could happen. So if the popularities are known, that means that t goes to infinity. So I have enough time to see to be able to have reasonable statistics about the nuance. Then, and if the number of edge caches, if the number of local caches go to infinity, we can compute the maximum expected hit rate that one can have. And this is kind of, the result somehow is has like this theta L that arises here, and this is kind of has a threshold flavor to it. And so what this tells us is that if you know relationship between locations, then you can leverage those relationships to improve hit rates by accumulating the data that you have between those. So, in fact, sort of these are ingredients that we actually packaged together to come up with a solution that we propose to people who are interested in doing this, sort of the production lines at Huawei. So the solution we propose is the following: is that to use some kind of knowledge about the location, be it some features of the location, income, whatever, and knowing historical traffic to cluster those caches, and then use what's the clustered ABT, so age-based thresholding, and we use like a two-step approach. So we have a step that is local, and what it does, it is going to assume that it's going to be optimistic. Sorry, this one is, it's optimistic, so it just discards content that's not being asked for enough locally. So just that prunes the content. And then you perform RRU on the rest, and from time to time what you will do is that you'll be sending data to the controller, and then figure out that there are very, very popular contents that are popular among all the caches, not the local caches. And those will be prefetched. Okay, so this is something that might have started early in some neighborhood, then the controller learns about it, and then sort of decides that those are worth replicating everywhere. And so this is the solution we proposed, just to show you what the results are. And this is what sort of we kind of show to the engineers to convince them, is that if you want to use the simple RRU to do caching, then you'll be really, really hitting very rarely. Then doing chunking is just really just here scaling the storage content. And here this is just doing learning globally. And this is like the exploit the locality, which is the algorithm that I just defined, which kind of takes into account of something which is globally popular and things that are locally popular, and then mixes the two to be able to respond to the problem. So I'm going to stop here. Thank you.
Thank you very much. Questions? Maybe it's a small detail, but the knowledge about the popularity of the content remains constant for a while and then stops. Could it not be addressed in a different way, where there is some aging of the interest into the data?
So doing simulation, we looked at various aspects, that there is aging, or actually there is sort of ramp up and then aging, which is often what you observe. It's obviously very difficult to handle the analysis, but you could do sort of if you knew the behavior, like for example, how quickly it becomes popular, how quickly it fades, then you can sort of tailor this algorithm to that.
And let me insist a little, there is a connection to combinatorial bandits, where actually you want to select several ads at the same time. Did you try to
So what we're looking at, I was saying earlier to Sebastian, there is an issue to explain to engineers bandits. So it's really kind of, for them this is a magical, it seems to work in theory, but they don't believe in it in practice, and they're trying to convince them. And so the issue here, so the issue here is like, even if you look at it from a bandit perspective, I think it's a different, you have like multiple learners that are different locations that are seeing finite versions of the processes. And so I don't know how to deal with that in the first instance.
Can be combinatorial.
Yeah, so yeah. Anyway.
Thank you. There is another question.
This is an application question. Do you know if there exists application of such practices in trading, for instance, in distributing materials between various places for globalization, on reducing cost of globalization, reducing the transport costs, and optimizing the matching between the offer and demand in the trading domain?
Are you asking me whether there are applications of this in trading?
Yes.
I know very little about trading, to be honest, but I know that there is applications here, and so the earlier talk were about sponsored search. So now what we're doing is we're trying to do sponsored search, but in urban environment, not only in a computer, but you have like you have places where you can put ads, and now you want to put ads that are the most relevant to the local crowds, and sort of this is the only other application I can see, which is something we're working on. But I don't know about
Yes.